Hello and welcome to this VPAL Signature event. Harvard Speaks on Climate Change. Green Building Design in the Age of Renewables is brought to you by Harvard's Office of the Vice Provost for Advances in Learning and the Salata Institute for Climate and Sustainability in partnership with the Harvard Alumni Association. Vice Provost for Climate and Sustainability and Director of the Salata Institute, Jim Stock, will host. Without further ado, Jim, the virtual floor is yours.
Thanks so much, and good afternoon. Welcome to this edition of Harvard Speaks on Climate Change. A core objective of the Salata Institute is to drive impactful research by Harvard faculty and students on climate change, sustainability, and the energy transition. To that end, the Institute supports cross-school research on climate and sustainability topics with focus on impact at scale. Harvard has many accomplished faculty members across its schools engaged in research and thinking on the frontiers of tackling climate change problems. This series provides the broad Harvard community an opportunity to learn about their work. We take you on a virtual tour of the research and engagement being done here on climate and sustainability. Each hour focuses on a different topic, featuring one or two faculty members. Today, we learn about exciting recent advances in the design of buildings for the energy transition. Buildings use a lot of energy for heating, cooling, and lighting. One way to reduce emissions is to use less energy for those purposes, both in new buildings and when old buildings get renovated. The world of green buildings is changing rapidly, however, with the advent of new technologies and with the recognition that an increasingly large fraction of power will be generated by renewable energy, which in the case of photovoltaics has a strong daily cycle. We're fortunate today to have two guests, both from Harvard's Graduate School of Design, who are working on different parts of this dynamic and important field. Jonathan Grinham is an assistant professor of architecture. Jonathan's work merges advances in material science with building design to address energy use and life cycle carbon emissions. Holly Samuelson is associate professor of architecture. Her current projects harness advanced building simulations to investigate issues of greenhouse gas emissions, heat vulnerability, and indoor environmental quality while considering the future of buildings in a changing electricity grid. With that, let me turn this over to Jonathan.
Well, thank you, Jim, for the invitation. Of course, thank you for the Salata Institute for having us here today. I want to talk about kind of an innovative project that we've been working on for many years, which will go under the name VESMA, and recently has kind of spun out some of the related technology into trellis air. And this technology is really a highly interdisciplinary study. I'm fortunate to work across the Harvard campus with really many different bright people from the Graduate School of Design, the Center for Green Buildings and Cities, the Wyss Institute, the School of Engineering, as well as others at other universities and national laboratories and industries. And the research I'm going to be sharing today is driven a lot by collaboration with Professor Joanna Eisenberg at the School of Engineering and Applied Sciences, as well as Jack Alvarenga, a senior scientist there. And we're going to be talking about kind of the problem of cooling. So as architects love to do, we like to carve out our kind of niche in the world of climate change and global warming and say we're a part of the problem. And one of those issues is that the greenhouse gas emissions associated with space cooling of our buildings, represents about 4% of annual emissions. And a lot of this is driven by the fact that the refrigerants we are using currently to cool these spaces have extremely high GWPs, global warming potentials, upwards about 1,500 times that of a single molecule of CO2. And so we're also seeing that as the world is kind of warming, as the map is showing, we're going to have more and more adoption in areas that are hot and humid. And so taking on that question of the energy spent to cool in those spaces, most of that energy, about 80%, is actually driven by the moisture in the air, not necessarily just the temperature. And so if we take this kind of question put out there, the notion that we have a lot of high GWP refrigerants in the process, we can take this 4% number, which comes out to about 2 gigatons of CO2 per year, and recognize that if I say we want to reduce these emissions, it's not necessarily just a question question of what is my set point, what is the temperature I'm trying to achieve, but instead we have to look at the emissions in this kind of 1/3 model, where about 1/3 of our emissions are coming from the energy used for cooling, 1/3 of it's coming from the energy for dehumidification, latent heat. So how do we actually remove moisture in there so we feel less sticky, so our bodies can properly perspirate and cool ourselves off on top of other technologies that need that humidity reduced. But that other major third of that load that we're typically not thinking about is the refrigerants, these high GWP refrigerants that leak in the manufacturing of the AC unit. They leak during the life of that AC unit, and they leak at the end of that unit. And so I'm going to talk about a few technologies that take on this problem. But first, I'll at least go back and say that if we talk about where this expansion is happening in areas like India and China, we're going to see nearly a 3-fold increase in the amount of cooling we're going to desire. So we have these emissions related to cooling, but they're also expected to triple by the kind of climate goals of 2050. And so this is a problem, but it's also for some of us an opportunity to say this is a very large market. It seems to be a market that is controlled by a few groups, but in reality, there's opportunity to advance new technologies in this space. And so we'll talk a little bit about that at the very end. But the first technology I want to talk about is CSNAP. This is a technology that's been supported by the Wyss Institute as well as the Harvard Climate Change Solutions Fund. And this is an indirect evaporative cooler. So evaporative cooling is something that humans have used for quite a long time now. It's something we use to cool our own bodies. And we're looking at a way of doing this within ceramics, doing indirect evaporative cooling. And so one of the major kind of technology breakthroughs that we have is that we use a ceramic body, a ceramic heat exchanger, as a porous media to hold water, and that water is used in the evaporative cooling process to cool the air. But what we do is we introduce this kind of rationally controlled barrier layer, in this case in the form of this a Boehmite kind of nanoscale structure that you see in this image, this flaky morphology that we then functionalize and are able to control areas of the ceramic where we'll have completely dry ceramic or wet ceramic. And this allows us to bring about the idea of an indirect evaporative cooler. So we've worked with ceramicists in Spain to actually manufacture the exchange unit you see in the image on the right. And what we do is we take these different channels and we coat them so that some are dry using our barrier layer, meaning dry air moving through them, and then some are allowed to be wetted by a misting system. And through this geometry, we introduce something called a sub-wet bulb regenerative indirect evaporative cooler. So we can bring in outdoor air. That air passes through the treated channel where it becomes sensibly cooled by the channels next door where the evaporation is happening. Some of that now cool air enters the building, but part of that air is then regenerated and brought into the wet channels to allow us to cool below the wet bulb temperature, which is the typical limit of a normal evaporative cooler. And the key here is that if I use a typical kind of swamp cooler as the technology, I would be bringing in cool air, but I'd also be bringing in a lot of moisture with that cool air. And so for one, it might make it uncomfortable, or two, in cities like Boston, it may not work that well because I'm limited by that wet bulb depression, the difference between the temperature I want to achieve and what that the wet bulb of that actual temperature is as well. So this allows us to kind of produce a more powerful cooling system enabled by this barrier layer. And so we've done a lot of work actually field testing and proving it out. 2 summers ago, we tested the system at the Center for Green Buildings and Cities House Zero. We pulled out part of the wall section and installed the unit and tested it over kind of a record heat wave in Boston for a series of 2 weeks. And we're really happy about some of the kind of press we got, but we're also really happy about the results. We showed that we could do about 1/2 ton of refrigeration. So this would be equivalent to a typical AC unit you might put in your apartment, but we could do that at a much higher efficiency than a typical vapor compression unit, and we're also providing 100% fresh air. And in this case, our refrigerant, our phase change is water, so we have no high GWP gases, and we're using that water very efficiently. So at the same time we're developing this technology, we were also funded by the Department of Energy and again the Harvard Climate Change Solution Fund to develop a different way of cooling. This is dry screen, and this is looking at the latent heat, the dehumidification side of cooling through a vacuum membrane dehumidification system. And so in this case, we're really taking on that emissions load by the refrigerant, but also latent heat in the airstream. And what we do is we're using a very kind of special water selective polymer. This polymer is water soluble. And so it will quite literally pull water molecules out of an airstream passing the membrane. And then we apply a vacuum pressure to that membrane and quite literally just suck out the water molecules. So this is a very interesting process where instead of using condensation like a typical system would, we're using a selective membrane that's only pulling water molecules out of that air, and isothermally, meaning there's no actual heat exchange happening, isothermally reducing the humidity load in the air coming in. And we do this through this kind of specialty polymer system that allows us to kind of maximize the vapor flows through the system. And just like before, we go out and test it. In this case, we went to a more humid climate at the University of Miami in Florida, and we tested this in an old 1950s building. It's kind of the perfect example of also thinking about retrofit solutions to our existing building stock. This is a system that only uses a typical AC window unit. It's meant to be naturally ventilated, but has been closed up ever since. And so what we're showing here is that we're testing the ability for this particular system to dehumidify, but we're also looking at the kind of thermal health benefits. So in this case, in Miami, we might be able to bring in a much warmer outside air and then dehumidify it and still hit the comfort specs that we need to have. So we're actually eliminating the need for cooling in some situations while being able to bring in fresh air because we're just dealing with that latent load or the dehumidification of air. And again, we had really great results showing that we could hit the specifications needed in that field of dehumidification while bringing in 100% fresh air, no refrigerants, and hitting those target energy reductions, especially without needing to sensibly cool the air. And so if you're playing along at home, you might go, hey, there's a good opportunity here. And that opportunity is the technology that I introduced, that's VESMA, where we actually combine these two. So I don't want to go too deep into it, but I always like to at least put one psychrometric chart out there. And the psychrometric chart on the right lets us kind of understand how vapors and gases perform thermodynamically in buildings. And this is what Willis Carrier invented 120 years ago and kind of is the way we've been doing things ever since. But in this case, what we're thinking about is the ability to use the dry screen system to dehumidify the air before it comes into a building. And now that we have a drier air, we can use the CSNAP system as an evaporative cooler to its maximum potential. If we have more dry air and we're evaporating water into that dry air, we have a greater cooling potential because we have a lower wet bulb limit. And then the indirect aspect of our regenerative system allows us to get even below that. And so once again, we combine these systems, and I'll play a short clip of a video where we again took this technology, now the combined VESMA technology, back to House Zero to test it in the live lab there. And in this case, we combine the two into a kind of a smaller unit. We're not using ceramics in this case, just to quickly prototype the system. This is always awkward seeing yourself talking in a presentation while you're talking, but it gives you kind of a run through of what we're doing, kind of this idea of the initial system using that barrier layer, and we can actually see it rejecting water there. And then the ability for that ceramic system to cool. But in the case of the VESMA technology, we combine the two. So we bring in fresh air from the outside, we dehumidify it, and then we cool it using indirect evaporative cooling. So you can see part of the systems here. We tested this again for about a 2-week period against a number of different specifications, and the results were extremely promising. One thing is that the overall system has a kind of coefficient of performance around 4.3. That's probably on the typical end of a well-performing AC unit. But what we're also showing is that combined, we have a lot of potential, right? The indirect evaporative cooling system performs extremely well. It can cool below the wet bulb temperature, and ultimately it can also hit extremely high efficiencies because we have been removing that latent heat in the system. But one of the other exciting parts of this is that we're collecting water as we dehumidify. So air comes past our membrane system. We put a pressure on that to create a concentration gradient. We extract out the water molecules. We don't pull across air molecules, and we end up with water collection. And so we show that the system can collect upwards for a very kind of small system on the order of about 8 liters per day. But when we start to think about the water being used for evaporative cooling, and the water we're collecting, we show that we have the potential for a water generating system, wherein if we balance the flow of air coming into the building through the evaporative cooling unit and through the dehumidifier, we have the potential to actually capture, under the right conditions, more water than the evaporative cooler uses. So we're also thinking about the other externalities of water usage in different resource scarce environments. So it's another kind of benefit of the system, while we also achieve these other marks of performance. And one of the kind of interesting aspects of this is that a lot of this is being driven by the ability to pump down vacuum on the system. And as we think about where could this technology go as we start to scale it up into larger tons of refrigeration, something more kind of akin to a large house or a commercial unit, maybe a rooftop system, we start to see the efficiencies of our system grow. And so we expect to anticipate a much higher coefficient of performance. And this is a term that basically says for every watt of electrical energy we put in, how much wattage of thermal energy out do we get? So something above 1 is always good. And so we start to really push the limits of that. And so ultimately for Vesma, we have some kind of takeaways from the project. We, of course, talked about a well-performing system where we're hitting on these energy efficiencies needed to drive down related electrical emissions, this potential for water regeneration, the big key aspect of this of not using refrigerants in the process, and then the ability to hit special target markets and improve the performance in those markets. And so ultimately, with all this information in hand, we've worked really closely with the Office of Technology Development at Harvard, specifically Chris Petty, who's done an amazing job with our team to help us get this technology out into the world. And this year, we formalized Trellis Air, who will be using some of these technologies to be looking at possibilities of dehumidification in buildings. So we're really excited to not only be speaking about the potential of this research in a laboratory or the Harvard University system, but really driving the technology out into the environment, into the industry, and hopefully providing real climate change solutions. With that, I will just say that I do have to thank my close colleague, Jack Alvarenga, here in the image with me, and a number of other really important collaborators on this project, as well as a number of other universities, institutes, and industry partners. So I will end it there. And again, thank you, Jim, for the invitation.
Thank you. Holly, you're up.
Thanks so much, Jim, and thanks, Jonathan. My talk is optimizing window glass properties in a changing context, so thank you for joining me. Thank you to our funders and to my amazing team, Amir Baniasati and Charu Srivastava. So first, some trends. Solar power accounted for nearly half of new U.S. electricity generating capacity in 2022, and solar is estimated to meet 20% of U.S. electricity use by 2050. Perhaps we could make it more. A challenge to this growth in electricity generation from intermittent sources such as solar is the problem of misaligned electricity supply and demand. So what we're showing here is the infamous duck curve. So a typical spring day in California, and you can see how it's changed over the years as more and more solar generation has been added to that grid. The midday electricity load is not really the problem. It's really the evening load that's now the problem. Some other trends, we're seeing a massive incentive to switch from natural gas heating in buildings to heating with electric heat pumps. So here are two very recent headlines that show that last year heat pumps outsold gas furnaces in the US. And this has ramifications at the building level that I will get into, but it also has ramifications at the grid level. So another recent headline talks about how our grids, we're used to them being stressed in the summer when everyone's running their air conditioning, but not necessarily in the winter because we're heating our buildings not with electricity. But that's expected to change, and some experts think that the winter peaks might outstrip anything that we've seen from the summer peaks in cold climates. So for new buildings and for major retrofits of buildings, we have building codes that mandate that performance. And we have energy codes that mandate things like how much insulation we should have in our buildings and window properties. And window insulation values get a lot of attention, but what I want to talk to you about is solar heat gain coefficients. So how much heat from the sun is allowed to penetrate through the window. Now, in these building codes that underpin our local codes, large residential buildings are grouped together with all commercial buildings. And office buildings and other commercial buildings often have a lot of heat generated inside of them by things like people and lights and computers, whereas residential buildings just have less free heat like that. We need more heating from your heating system, basically. Another thing that shows up in most building codes is that windows are the requirements for windows are the same for all windows, no matter whether they're facing north, south, east, or west. So I think this matters. I think that windows affect the timing of energy use, and I think that that is something that's newly important. So what I'm showing here with this window diagram is that radiation from different wavelengths is hitting the window, and we have specifications for our glass about how much light transmits through, and we generally want that to be a higher number. But we also have specifications about how much of that incident heat on average is allowed to penetrate through the window. And building codes usually set a maximum value for this. So in large residential buildings, in our climates and colder in the US, we have a maximum value. And in our climate, Boston and similar climates, we even have a maximum value for small residential buildings like our homes. Now, even if you're not following these prescriptive requirements of the code, you can run an energy simulation to do whatever you want and show that you're being energy efficient. And building simulation is the methods that we use in my group. So what does that mean? It's a physical based model of a building. So we calculate all the different heat flows in the building based on first principles. Now, common practice that I've seen over and over again in so many reports and the underpinnings of our building code are that you test out different properties. So example of this project that I did years ago with my team, here we are testing the solar heat gain coefficient of different windows. So we're testing window 1 versus window 2 versus window 3 versus window 4, and we're seeing which window gives us the best energy performance. And it's typical to consider all the orientations the same because you're also testing, thousands of other things, and it's just easier. But I'm going to call into question that practice. And generally, lower solar heat gain coefficient is usually assumed to be better. So over and over and over and over again, when you see in green building reports and standards, when you see the windows that are good, better, and best, they're getting to be more insulative, less leaky, and they're always lowering that solar heat gain coefficient. By the way, I am a fan of overhangs, especially on south-facing windows, and our ideas would work even better there. But because they're not mandated and most buildings don't have external shades, we're looking at the worst case scenario here, which is buildings that don't have external shades. Okay, so your windows in a mixed hot summer, cold climate are a compromise between optimal summer and winter performance. Now, without buying really expensive electrochromic glass, if we just have normal windows, you have the same glass year round, and you kind of want more heat in the winter and less heat in the summer, but you're stuck with one glass. So it's the codes or it's the building simulations that are telling us what kind of glass we should pick. And this is important because the windows that we pick today will be in place for decades. This is an expensive choice to buy windows. But then getting the right windows in what I'm talking about is not necessarily more or less expensive. It can have a difference in cost, but it doesn't necessarily cost more to make the right decision here. So since we're spending a lot of money on the windows that we're putting in, we need to get them right because they're going to last for decades. So here are my study questions. Should we consider this changing context in architectural design? Can changing window design help align energy demand with clean energy supply, or at least get us within the season, so that if we need to buy storage, we're not trying to store energy from one season to another. So here's the specific question that we're studying today as a case study. In south-facing residential windows in cool climates, could a higher solar heat gain help reduce energy use and carbon emissions? In other words, could us as architects and us as building owners making choices about our own buildings help to flatten that duck? So our study method, we simulated archetypical code-compliant mid-rise residential buildings, and these are models that are made by the U.S. Department of Energy. These are the models that are used to make the model energy codes. So we're using the same things with two exceptions. I want to look at the future of buildings, so we're looking at an all-electric building with heat pumps. And also, we tested a range of behaviors. The codes are based on the worst possible behavior with lots of electronics running all the time and people not making good decisions at all about opening and closing windows and blinds and lights. So here I'm just going to focus on one version. And here's the crux of it. We're testing different windows. So the solar heat gain coefficient from 0.2 or 20% transmittance to up to 0.8. And we're looking here at the south-facing apartments. The results would hold true in near south-facing windows. And so we're trying to optimize for different design objectives here. 1, save energy. We want those utility bills to be lower. 2, maybe someone might care about saving non-solar energy. What if you have photovoltaics? And so you want to say, I want my building to save energy when I have to buy from the grid. 3, saving peak loads. So that's that moment in time when your building is drawing the most power from the grid. And that has ramifications because it affects your heating and cooling peaks, affect the size of your heat pump. You don't want it to be bigger and more expensive. And when a group of buildings do this, it affects the peak draw on the grid. And finally, saving carbon emissions, which is kind of a new goal, believe it or not, when thinking about building design. So our study methods are, we looked at this in 19 cities, but first I just want to focus on 3 cities, the one we're in and one slightly colder and slightly warmer. And I want to show you a number of trends. So there are a number of temporal trends going on with both windows and solar generation and heat pumps, and that's the crux of all of this. And so I want to just demonstrate what's happening over time. We can't just add everything up and on an annual basis and go with that, like we have been. So here I'm showing the 3 cities, and what I'm demonstrating is how much radiation is entering from a south-facing window. And I'm going to show these graphs over and over again. Across the bottom is the months of the year, and then the y-axis are the hours of the day. And so here, the red means that's when the most heat is being emitted. And you'll notice that it's not in the summer for south-facing windows. It's actually in these cities in these cases, January and February. That's for the south-facing windows. And the reason is because if you think about the sun angles, when it's coming from the south in the middle of the day, the sun is very high in the sky during the summer. And so those angles, that radiation tends to glance off of the glass more than when the sun is low in the sky in the winter and it's penetrating through. So near south-facing windows are pretty special for us. Okay, so what happens if we were to change this? So here I'm plotting the change if we went from 33% solar heat gain to 65% solar heat gain windows, just to demonstrate the difference. Across the top, I'm showing the decrease in heating demand and the increasing cooling demand. So this is how much, I haven't applied a system yet, this is how much heat or cooling your building needs. So a few things to notice here. One is that the red is good on the top row. There's a decrease in heating demand even at night when the sun isn't shining. I haven't done anything special to this building. This is just due to the heat that is stored by the normal floor and walls and the things in the building. So when you've got that sun penetrating in the middle of the day, it is helping to save energy even into the night. Okay, admittedly, the cooling demand has increased, as you might expect. In the summer, you let more heat in through the windows. So you might be thinking, this ain't good. But there's a few other things going on. So we're focusing on buildings that are using air source heat pumps, which is the main new method of heating and cooling buildings. They have to work harder at more extreme outdoor temperatures. So the colder it is, the less efficiency you get with your system, and the hotter, the same thing. Just the laws of thermodynamics. So here, what I'm trying to show in these cities is the outdoor temperatures at the top, and then at all those moments of the year, what was the coefficient of performance of the heating system or the cooling system? And I know it's not very easy to read here, but what I'm trying to say is that the heating benefits, when we change the glass, often occur at times of low efficiency for the heat pumps, whereas the opposite is not necessarily true for the cooling detriments. It's not as well correlated. Personally, I'm feeling better about this, but what else? What about when can solar panels produce? So what we're plotting here are the temporal patterns of a photovoltaic panel production. And you might see kind of a familiar pattern. So here, when we changed the glass, we increased cooling, and it has some correlation to when a solar panel can produce. Okay, but someone could say, not all of the electricity that we're going to be adding to a grid is meant to be solar. So here I'm looking at a different case. This is from National Renewable Energy Laboratory, their Cambium data set, where they're showing long-run marginal emission rates. So this is a mid-case rate. And I don't really have time to get into all the details, but there are different ways that you can predict carbon emissions. This is one of them, and I think it's a good corollary to looking at energy use. So you can see that there's still a pattern here. And so it still kind of resembles when we would be increasing that cooling load. It's still when the electricity on the grid is meant to be cleaner. That's when we would be using more cooling energy. So what I'm trying to say with showing you the patterns of solar panels and the patterns of the marginal emissions rates, long-range marginal emissions rates, is that the penalty in cooling demand with our glass, or this new glass, mostly happens at times when the solar energy is abundant for clean power generation and marginal emissions are cleanest. So what happens across our 19 cities? Well, in the warmer climates over on the left, climate zone 3 and 4, we're okay. What we're trying to show on the y-axis is the optimal glass. And what we're showing in red, so typically people think the rules of thumb are that lower is better for energy performance. And the codes allow a maximum value that's shown in red. So in the warmer climates, no problem. But in the colder climates, if we're looking at either minimizing annual electricity use or minimizing non-solar electricity use or minimizing those long-run marginal carbon emissions rates, the old adage that lower is better does not hold true. And actually, we might want these windows to be much higher than what would be allowed by prescriptive code. So here's the actual energy results to see how much energy we save for heating, cooling, and lighting for the different cities. And so you can see, energy's on the y-axis, glass that we're trying is on the y-axis, that there's kind of a sweet spot. So this is a sweet spot for saving annual electricity use. And in these cool climates, it is higher than code allowable or than typically expected. And it's the same idea if we look at carbon emissions. And if we're looking at non-solar electricity, the higher the better. Okay, so it works out annually, but the concern is always, what about peak loads? We don't want to have huge systems. We don't want to overwhelm the grid. Well, in the cold climates, it turns out that works out better too. It's a win-win. So what we're showing here are the annual electricity demands for one of these buildings in Chicago. And you can see that the winter peaks of electricity demand are far outstripping the summer. And so our glass, if we change it, is actually helping the overall peaks. It's helping those winter peaks. And it's slightly hurting the summer peaks, but that's not driving the size of the grid generation or the size of the HVAC system. So in summary, by optimizing the solar heat gain coefficient of the glass in the cool climates compared to the best allowable by code or rules of thumb, we get 0 to 25% savings, depending on what our goal is. So here with the CO2 emission savings were 1 to 12%. Electricity savings were up to 6%. And this was very exciting to us because if you're trying to save energy in these new code compliant to today's standards buildings, saving 6%, we spend a lot of money just to save 0.5%. So these are sort of big numbers. So we were very excited by this. So summary, passive building design can impact emissions timing. More solar heat gain can improve heating loads and worsen cooling loads, but it's sort of happening at the right times. And contrary to assumed best practices, a higher solar heat gain coefficient may be preferable for south-facing windows in cold climate residential buildings. So this is what I did in my home. So what I mean is considering window orientation matters. So we should be doing this in practice, considering different windows properties on different north, south, east, west orientations separately. Thank you.
That was great. So I'm going to start. We have some good questions in the Q&A stream. We'll get more. Could you explain to me what the coefficient of performance is? So you both use that, but I'd love to have a definition. And why is that a relevant concept?
Sure. So it's for every unit of electricity that you use, it's how many units of heat that you move. So we've learned in physics class that you can't have more than 100% efficiency, but a heat pump's not trying to make heat, it's trying to move heat. So for 1 unit of electricity in, you can be taking from the outdoor air more than 1 unit of heat and moving it in, or in cooling mode, more than 1 unit of heat from your building and moving it out. So higher is better. Higher
is better. Okay. All right. So that's the same concept of coefficient of performance that you're using, Jonathan, in yours. And I have one more sort of just a technical question to make sure I understand, Jonathan, your system. If I understand it right, it's important to have these 2 parallel shafts because what's going on in one of them is that you're getting the evaporative, it's wet or you're wetting it, and there's evaporative cooling, and that's cooling the entire ceramic block, and air is flowing through the other one, and it's saying it's kind of cool as it flows through, and that's the mechanism for cooling the air. Is that right?
Yep, correct.
Okay, so then where's the energy used? So it's actually, if I want to think about it a little bit, it's kind of like a heat pump type concept, but just in a different way. But where is the energy being used in your system? It's got to have a fan to blow the air through, presumably. It must have some water circulation system, and maybe you could explain that a little bit.
Yeah, exactly. And the energy draw is quite small. We have really simple pumps to irrigate or mist the wetted side of the channel, and then fans to push air through that. And the big energy saving is that within a refrigerant system, you have to do compression, right? You're effectively getting the evaporation of that refrigerant, and then you compress it back down. And that's the work, the energy put into the system.
And the basic idea is, I bet many of our viewers have been in the Sierra Nevada in the summer, and it's 80 degrees, and you want to put on a sweater or something like that. But if they're in Boston in the summer and it's 80 degrees, you're not going to be wearing a sweater. You're going to be wearing your shorts, and it's kind of sweaty. And that's sort of the basic idea at play here, is if you can just get that air a lot cooler, you're going to need to have less of the compressive heat cooling or the other types of cooling. Is that right?
We bring in the ability to dehumidify it so we can feel comfortable.
From the first part of it, and then you can do the cooling through the ceramics.
Yep, exactly.
Yeah, okay, great. Because you talked about these moments that there's going to be these thermal characteristics of the building materials, Holly, that's going to affect the performance of the windows, I'd have to guess that actually your analysis maybe depends on what those building materials actually are, the thermal characteristics of the building materials are. So is there another dimension of optimization there? And I ask this because I think, Jonathan, if I remember correctly, that's something that you've worked on too. And so it seems like these are very different problems. What do you build a building out of, and what do you may build a window out of? But maybe they're related. And so maybe you could comment on that.
Sure. So we just tested this with a typical building with typical building materials, and we showed that, the effects, the solar heat gain was helping us into the night. You can easily store more thermal energy in a building. We could put, big jugs of water in the building, or we could phase change materials are more expensive, but we could easily store a lot more thermal energy to really help us to keep that solar heat gain for hours and maybe even beyond hours, days.
Jumping in on that, a little bit similar to the way Holly's kind of looking at convention. We published a few papers that also look at to what limit would we use building materials as a thermal storage device. Fundamentally saying that convention in architecture might have said that a lot of concrete is good in order for us to have that thermal inertia, that storage in a building. But when we start to look at the embodied emissions, those are for some called scope 3. We call them embodied, meaning the emissions related to the entire life cycle of that product. So extraction of minerals to then generate the cement, the CO2 production and clinker. When we start to kind of look at the embodied emissions relative to the gains from offsetting some amount of cooling or heating through thermal mass, we're pointing to some literature that says that thermal mass, just for the sake of thermal mass, may not be the right moving forward in architecture. If it's inherent in the structural capacity of that system, it makes sense, but the additionality only adds a pulse of carbon in this really critical time in kind of society and existence.
So thermal mass for the sake of thermal mass using materials like concrete.
Yeah, the papers look at a number of different kind of ways of applying it, but correct.
So there are a number of questions about the costs of these things. And I think that, when normal consumers think about green buildings, they think that sounds like a great idea, and then they kind of think about their wallet and they sort of worry a little bit. And certainly in an institutional setting, costs are often an important consideration, not the only consideration, but an important consideration. To get adoption of technologies, we've seen this with photovoltaics. I mean, photovoltaics were around for a long time. They're expensive. Now they're not expensive, and now they're really being adopted. There's some tax credits that are helping out, but basically it's fundamentally the economics. Yours is a computer simulation, Holly. I guess you've done it in your house, but yours is a computer simulation, and Jonathan, yours is still sort of a lab scale type thing. And presumably there's a lot more learning you could do, like maybe different ceramic combinations or modifications of the film or something like that. Are there reasons to think that these have the potential for actually being cheaper than standard approaches?
I think so. And we're starting to look into that. Okay. So I'm talking about new buildings or major renovations where you might want to replace the windows anyway. And so now it's a question of, do you go with a high or a low solar heat gain coefficient? And I'm still trying to maintain the same insulation values, which, by the way, it is a little bit hard.
The same R value. The same R value,
the same R value,
window.
same U value, however you want to call it. Yep. We have only tested products that are actually available. So you actually can meet the insulation values of the code with these solar heat gain coefficients that we're showing. And so I'm looking into how much difference this would cost. But I think compared to other measures to save energy, I do expect this to be cost effective. I really do.
Because of just the energy savings that you'll make over some reasonable lifetime that it could be amortized. Yeah.
Yeah. And I do actually think there might be cases where the windows I'm suggesting are cheaper than the windows that would have otherwise been used. To be continued on that. Now, in existing buildings, it's interesting because the idea would work better. So there's more heat loss in existing buildings because they're older, they're not as well insulated, but you already have windows. So can I save you enough money to pay for ripping out a window and replacing it? Maybe not. But if you're putting in a much more insulated window that is less leaky, and so people are already replacing windows anyway for other reasons. So I'm saying while you're buying that glass anyway, take into consideration your free heat gain in the winter.
That's great. How about you, Jonathan? I mean, building those ceramics must be very expensive because everything is really custom at this point, but one can imagine, is there a way to think about economies of scale or something like that in these contexts? And
in reality, I mean, ceramics is kind of one of our first design materials and one of the cheapest materials to produce at mass. And many of the kind of materials going into the special barriers we know are extremely cheap just alumina. These are things that are readily available. Even some of the specialty polymers that maybe 10 years ago were expensive and only within niche markets being used, specifically around like medical devices, are now in our tennis shoes and kind of in an everyday experience. You're probably wearing them, some of them right now. So those things have dropped off just by market trends. And then some of the specialty equipment that we need, again, is a similar case of maybe looking at a field adjacent and saying, okay, well, what would it mean to translate that into building technology? And we are up against, again, 120-year-old technology. So the fact that we can go out to a Home Depot here in Cambridge and buy that AC unit for $500, that's actually quite remarkable that we have kind of distilled that technology to such an expensive piece of equipment. So it is a challenge to kind of compete with the legacy system. But there are other kind of benefits and ways that we're thinking about it in terms of installation costs as well. I will say Holly and I are collaborating on a paper. We're using House Zero as a test bed to really to tackle that exact question that you have, not only for the test bed of House Zero, but across a number of simulated cases in the U.S. So that's something that's on the research agenda.
Why don't you briefly say just a word about House Zero, which is an asset that we have here on the Harvard campus, which is, pretty unusual.
I'll say one, it's a great example of retrofitting existing buildings. So I think a 1920s house that the Graduate School of Design acquired was using, and then working with architects Noheta, the director Ali Malkawi, upgraded the building to look at how do we draw down the energy use in the building, and Ali, being a mathematician and a designer, really bringing in a lot of computation, sensing, and the ability, I think in his case, which has been really remarkable after its commissioning, is also how do we use data to better understand the ability to reduce energy. Like, we can really track where energy is being used, whether the assumptions are made in early schematic design are correct, and then kind of change the way that the house is operating. So he and his team have done a really wonderful job of really dropping the energy use of that building. And then we've also published on the kind of question of the total carbon balance. So how much carbon was put into the making of the building, the different kind of energy reducing technologies, and then looking at kind of how much those could offset without the use of GERD emissions in the future.
That's great. Thank you. There are so many good questions. I'm going to turn straight to reading the Q&As here. How are there all these all-glass buildings with no operable windows that are getting LEED Platinum certificate? Something seems wrong here.
I agree. I mean, in the first generation of LEED, there were credits for bringing in more daylight and views, and there was a bit of an overkill, and there was not as many credits given for energy. So now LEED has changed, and there are more credits given for energy. And the daylighting standards have changed, so there is kind of a cap. But in recent versions of LEED, you can still get away with it. But I think the industry is recognizing this, and codes and voluntary standards are realizing that we're now demanding higher performance.
Have you looked into energy saving potential of using movable window insulation? So I know there's a bunch of technologies, like, there used to be something where you shoot beads in the middle between two panes or something along those lines. And I remember when I was growing up, I was told to draw the shades when I left in the morning from home because it was going to be a sunny, hot morning, and we didn't have AC.
I think it's a good move. I mean, it's something that I do. I have the honeycomb blinds, so there's some R value to them, and I close them. I close them at night. So yes, I think that's a good strategy.
But that's basically complementary to yours. It's not a substitute, but it's complementary to the sorts of things that you're looking at. That's good treatment for the summer, but actually your issue is you want to get more of that heat in the winter.
Exactly.
Oh, this is a really interesting question. For either of you, can you share an example in a project where the incorporation of biophilic design resulted in an easier or more successful integration of renewable energy sources? And somebody needs to define biophilic for our audience.
I could do the easy part. So biophilic is the theory that humans love nature, and science has shown that we get a lot of benefits from, for example, views of nature. There's been proof that hospital recovery times have been shortened. Now the thought is incorporating nature into design. Can that be a good thing? And I have to say, I'm not really an expert here. Jonathan, can you think of an example?
Yeah, I'm like having a panic attack only because, a lot of the great collaboration has been with the Wyss Institute for Biologically Inspired Engineering. And of course, my close collaborator, Joanna Eisenberg, is famous in this space. And so if we consider not just biophilic, I think we're correctly saying biophilic, this kind of connection to nature, but we've done a lot of bio-inspired design as well, looking at kind of flow optimization that we might look at mammalian vascular systems and optimizing that. So if we think about this exchange within the ceramic, that harpens back to the way our own bodies exchange energy in our arteries and veins. But we do a number of different systems that we would say are extremely bio-inspired, from everything with the hydrophobic barrier layer to the form finding that we do to improve heat transfer. Nature's done a really good job of dissipating heat. It's kind of what it has to do. And so we use nature's inspiration in every project that we have. It's quite fun too to apply those principles. And
one thing I'll add is that I don't know if this is exactly biophilic, but it's using nature. Deciduous plants are really great for sun shading because you can have movable shades, and that's wonderful on your windows. Great, but they're expensive. So anytime you have a flat shade that doesn't move, the sun angles are symmetrical around the solstice. So you get the same sun angles on September 22nd as you do on March 22nd. But if you think about it, you might need cooling in September and heating in March. So fixed shades can only do so much. And like I showed, windows can do even less. But plants that lose their leaves, they tend to lose them at the right time on the thermal cycle. So if you have a tree or a vine outside your window that's providing shade, it tends to work really well.
Those sorts of benefits are often lost in common urban landscapes, and certainly in communities that, some of the communities with the oldest building stocks. So that's a really important observation. Going back to this biophilic or nature-based thing, there's a question that's relevant here for you, Jonathan. Have you tested materials other than ceramics, such as wood, which already has natural porosity and which is less carbon intensive to manufacture?
For this, wood is probably a whole nother talk when we talk about wood. I would also maybe point the attendee and their question to the GSD's website. We actually just had a symposium and right now an exhibition in Gund Hall that is looking at the future of the forest, led by our landscape department. We kind of, as architects, are really seeing anything in that field as an opportunity to kind of think about building better with our materials. And as much as we want to talk about wood in buildings, we have to really think about it more as a forestry practice and how those forests and those ecologies are sustained. So yes, we think about it quite a bit for the built environment. Specifically on this project, we have not looked at it, mostly maybe around some questions of hygroscopic behavior in terms of how much water is held within the wood and whether it releases at the right time. But there are some really fascinating projects related to kind of adaptive facades that might use that same ability for wood to absorb and the hygroscopic action and swelling of that wood to make automated kind of shading systems or ways of improving natural ventilation. These are a little more theoretical, but we've seen some interesting work in that space.
And in your defense, you have done testing with wood in your work on thermal storage.
Yeah, exactly. I mean, that test, we actually asked the major question because the industry, having pointed to timber construction as the kind of solution, I think we're all kind of stepping back and rethinking exactly what that means right now. Fundamentally, the idea being that the tree is going to store a certain amount of carbon. We can store that tree in a building, and we can consider, this is questionable, whether or not we want to say that's an offset or if buildings are storing carbon. And so we actually looked at that same question of thermal mass. So can we use really heavy timber construction as a way of holding heat because it's just on the outside limit of the right rate of diffusion, the rate of energy entering that material. And we found out that, yes, it actually can improve the thermal performance and the energy load of the building. And that research actually made us go, wait a minute, but concrete doesn't look that great. And so it actually launched other research in the space.
And one thing I might mention for your ceramic project, I also do research in mold. And so I'm not sure that I would advocate for having a wooden surface that's continually wetted and dried in airstream. Yeah.
Right. No, that's a good point. One of the things that I really like about both of these projects is, I'm sorry, as a non-architect, I often hear words like LEED and green, and I'm an economist, and so you end up saying, oh my gosh, this is just going to cost extra money, and that means it's not going to be widely adopted. It can tend to be boutique or selling into a market that's particularly interested in a green image. But one of the things that's so exciting about both of your projects is that this seems like something that, with suitable manufacturing scale, really could be cost effective and people would want to adopt just because it's going to save them money. And that seems to be incredibly important. I guess one question, Holly, for you, and then I think this is going to have to be our last question. You mentioned these standards. So it sounds to me like you you got away with it in your house, putting in these high heat transmissivity southern facing windows, but generically you can't really do that if there are building codes out there. Have you spent any time talking with the building codes people? So many of our problems in the energy transition, a lot of them are technological, but in some cases we have technologies that are feasible and work, and the problems are like the rules that we have in place in the institutions.
Okay, so two things there. So you can, so these are the prescriptive requirements. And that means that if you don't want to do anything fancy, you're just going to meet the letter of the law. These are the requirements. You always can do a performance-based approach where you run your own model, and then you can, the sky's the limit. You just need to show that, I mean, there are rules, but you need to show that your building can perform better than a standard building. So in some ways, to start with, I'm kind of speaking to the people that run the models and say, hey, try this and try these windows separately. I'm also, I think, eventually hoping to affect the methods that are used to underpin the codes and say maybe we need to be more granular and separate out maybe residential buildings, maybe separate out south-facing windows, because I'm not saying that this is a good idea for all buildings, but I'm saying that there is a substantial number of buildings that this represents where this can be a substantial improvement. And so I'd like to leave the door open for those. The other thing is, some of the philosophies behind the code is that the code's not meant to make good buildings. It's meant to avoid making the worst possible buildings. So if someone were to go crazy in the building, how bad could it be? And so I think, maybe we need to rethink the philosophy of our codes going forward and as we're trying to sharpen our pencils and defeat climate change.
That's optimistic, and I really think that's a great place to end this. So I'm so happy to have had this conversation with both of you. So thank you, both Jonathan and Holly, for taking part in this. I'd like to thank also the Office of the Vice Provost for Advances in Learning for their production support, and to the Harvard Alumni Association for their help with promotion and logistics. Finally, let me thank you, the audience, for joining us tonight, and I hope you're able to join us in March for our next installment. So let me now turn this back to our VPAL hosts.
Thank you, Holly, Jonathan, and Jim. Thank you all for joining us tonight. We hope you'll join us for more signature events. Information about our upcoming events, as well as the recordings of previous ones, can be found at vpal.harvard.edu/vpal events. Thank you all. Good night.